Hey guys, sorry for the long time between uploads. I'm actually busy implementing a case study for my masters, so that's taking a lot of my time. And I don't know why I always take on projects like making these videos when I have the most other obligations. Like during exam times, I'll take up the hobby of building coil guns and reading up on whales, but not when I have all the time in the world. But anyway, in this video we're going to discuss the tracking system, and in the video after that we'll do the control system. So the tracking system is responsible for figuring out where the turret should aim, and then the control system is responsible for telling the turret how to aim there. Wait. Okay. So like I said, the tracking system is responsible for finding the target and then figuring out where the turret should aim in order to hit the target. There's basically going to be two main parts to this. The first one is finding the target, and then the second part is figuring out where to aim. So like we said, finding the target is going to be done by stereo vision cameras, because other options like LiDAR is just way too expensive. And with cameras you get the added benefit of being able to see in color, and you can do a lot more image processing with cameras than with LiDAR. Since we're going to use cameras, we need to have some specifications for what cameras we're going to choose. And the two main things to consider when choosing cameras in this instance is resolution and frames per second. We don't care really that much about color depth or high dynamic range, and you can have more fancy cameras, you can have infrared cameras and stuff like that to enhance your vision of the target, but for this proof of concept it doesn't matter. So first let's discuss how we're going to figure out what resolution it has to be. So what we need to do is figure out what's the minimum amount of pixels that we need to make sure that we've detected a target or not. So say there's some noise, fluctuations, artifacts in the image that flickers on and off. What's the average size of those artifacts? Because surely we need a sample that's a lot larger than those artifacts. So doing a bit of research and taking various pictures with webcams, I found that usually you find high frequency noise in about the 1 pixel size range. So in other words, there'll be 1 pixel flickers white to black and then disappears, and then it's like a snowy haze. It doesn't matter too much. The frequency is too high to really care about. But then you get larger artifacts that are about 4x4 pixels that stay slightly longer, and I decided, well, I want to be at least 25 times larger than that. So in this image you can see how I highlighted some artifacts, and the minimum target size I then chose, which is 25 times the area of a 4x4 pixel. So then you have the minimum amount of pixels that you want to have the target made up of. This is now assuming is at the furthest possible range of the system. And since you know that, you can draw a similar triangle back to your image plane and then figure out, well, on the back plane it has a fraction of, say, 0.015. So on your image plane it should also have a fraction of 0.015. And then if we said that it has to have a minimum of some amount of pixels, you multiply the inverse of that fraction, and then you get the total image width and the total image height. So in this case, the minimum image width for a 70-degree field of view camera had to be 985 pixels, and the image height had to be 377. Obviously you don't get cameras in that range. The closest one is a 1080p by 720p camera, which is great because that's basically any webcam. It means we don't need a 4K or an 8K grand camera and then worry about the processing capabilities of handling all those pixels. So we're completely within range to use webcams for this. Okay, the method of detection. There's a lot of really advanced open source algorithms out there which does pose estimation based on machine vision and target tracking, making sure you're taking the same target, object identification. I mean, those things exist. We don't need to prove that they'll work with the system, and you can add them to make it better. But for this proof of concept, all we're going to do is background subtraction. So background subtraction is when you take a photo of the background and you store that image. And then every frame that comes in from the camera, you subtract that image from the stored image. So in other words, you take every pixel and you subtract it from the image that just came in. If the pixels were the same, that means the subtraction will end up being 0. And if they're not the same, there'll be some residue. Then you choose a threshold. If the difference is more than 20, then make it white. If the difference is less than 20, make it black. And that's called a binary threshold. So then you end up with the image like the one in the middle of this picture of my hand. And now you've detected something in the scene, but you sit with a problem. Some pixels of that target might fall below the threshold. And this is important for stereo vision because we're going to take the center of gravity of all those pixels and say that's the center of our target. And if you have two cameras and the one camera has a different, some pixels fall out in this camera but some pixels don't fall out in that camera, then their center of gravities might change. And because it's a stereo vision system, if both of the cameras don't see the exact same center on the target, there's going to be a distance disparity. So you need to find the exact same center on all the targets. In other words, you can't have these black regions that will change the center of gravity that it sees the target at. So what I did then was I took the outermost pixels of what I detected and I drew a polygon around that, and then I filled up the polygon. And when you fill up the polygon, you can get the center of gravity of that, and then both cameras will be pointing to the exact same center of gravity, or very, very close to it. So that solves that problem. And then here is a state machine of basically capturing the image, generating the data, and then finding the coordinates of the target. So using triangulation, say you found now the center of gravities of the target, you can use triangulation to find the distance the target is away from the cameras, as well as the pan and tilt angles from the cameras. And then with that, it's just basic high school trigonometry, you can find the XYZ coordinates of the target. So if this is an ideal camera, a pinhole camera, then the disparity equation, disparity just means the difference each camera sees a particular point in space to. So if the target was exactly in the middle, and this camera sits on the right hand side, and this camera sits on the left hand side, this camera will see it slightly to the right, and that camera will see it slightly to the left. That's the disparity. So a disparity equation relates the disparity to the distance the target is away. So if this is an ideal camera, pinhole camera with no lens distortion, and everything was set up perfectly, then it would follow a power law. So it'll be something to the power of something, which will be the graph that relates disparity to distance. But as you can see on the graph that I have here, the red line is the power fit, and it wasn't as accurate as I thought I could make it, so I did a XL fit of a symmetric sigmoidal curve. I'm not even exactly sure what that is. I think it's got something to do with statistics, but it fit my sample points way better. And with this setup, I managed to get an accuracy of up to or down to 10 centimeters at 20 meter range. So at 20 meters I could differentiate between here and here, which I thought was pretty good. I mean, I was bargaining on a meter accuracy, because I mean, what's the bullet drop of a paintball over a meter? It's probably like that much. Okay, so now you have your target in 3D space. When you get the target 3D position from the stereo cameras alone, that position is going to be very noisy. If your target is a pretty far distance away, even just the center of gravity of one camera flickering between pixels will probably send the distance estimation flickering between 10 to 20 centimeters the whole time. And most likely the flickering is going to be a lot worse than that. And by instinct, I assume that our noise range will be something about a sphere this size. That means it can go from anywhere from here to there in one frame, which is a lot. And we need to denoise that, because if you think about it, we're only going to take maybe one shot every 20 frames, 10 frames. So if you can take the average of all those 10 frames, then you'll most likely end up with somewhere very, very close to where the actual center point is. But just taking the average isn't enough, because that introduces lag, and that will simply just be a low pass filter. So a low pass filter would mean that if this is your target and it's doing this, then you're sort of ignoring the high frequency movements and only following the low frequency ones. But you'll see that it lags behind, which is exactly what we don't want, because if it lags behind and the thing's traveling this way, that means we need to compensate for the lag and aim ahead of the target, and that just introduces way too many inaccuracies. So what we're going to use is a Kalman filter. And a Kalman filter is just absolute magic. Like, it took me a while to understand how they worked, and it's actually really simple. I hope I can explain it well in this video. You don't need to know the math behind it, you just need to know how it does what it does. So essentially, you have two parts to the Kalman filter. One part is the sensor input, so that's what the sensors or the camera is telling it is happening. And the other part is the model of the system that you're measuring. So in our case, the model of the system for the human is actually very simple. We're just basically telling it that if he was at this position and he was going this fast, then the model predicts he would most likely be at this position plus this velocity. So it's a simple first order integrator. Your model will sort of be a reality check for what your sensors are telling you, which is funny because your sensors are actually giving you the real world information. But anyway, the Kalman filter balances these two. So if it sees that the sensors are starting to give really erratic readings and they vary too much, then it'll rely more on what the model's telling it. So what this means is if we give it some really erratic sensor inputs, the model will sort of adjust to say, well, I'm not going to listen to the high frequency noise, but I know that he was sort of traveling in this direction most of the time, so I'm going to keep going that velocity until it sees that this changed, and then it'll change its own velocity. So the Kalman filter is a very smart low pass filter which balances what it thinks the system is going to do next with what the sensors tell it the system is doing currently. So this should give us a very stable on target point estimation of where the target is. Okay, so since we have a very nice estimate of the target's position, his velocity and his acceleration, now we can move on to target leading, the gun laying algorithm. So to do this, we basically have to equate two things: the trajectory of the projectile and the trajectory of the target. So since we know the acceleration, the position, and the velocity of the target, that equates to a trajectory of a parabola. So a parabola, parametric parabola anywhere in 3D space. So parametric just means that you have time as the only variable in the x, y, and z components. So as you iterate through time, it'll change the position where the target would be along those time steps. And you have the same thing for the projectile. So you could do this by equating the differential equation with a iterative solver differential equation of the paintball, but we don't need it to be that accurate. I think the effects of drag is not going to be pronounced enough over 20 meters to take that into account. But what I did do is I ran 2 or 3 simulations of the differential equation of the paintball in space, one with the maximum muzzle velocity and one with the minimum muzzle velocity, and then based on the bullet drop I basically took the parabola which was between the two, so I sort of did compensate for the effect of drag, wherein I try to minimize the start and end errors when I fit the parabola. So now we have the equation of motion for the ball described in the second order polynomial, which is a parabola, and the same for the target. And since time is the common variable in both of them, and we know that time will have to be the same as soon as interception takes place, you rearrange the equations so that time sits on the one side of all the equations, and that means you can stick them together. So the x target position parabola and the x projectile position parabola both equals to the same time, and you solve that for all of them. What you end up with then is one Moore's equation that is a fourth order polynomial with obviously 4 roots, and those roots represent where the intersection times will be. So, interesting point, the reason it has 4 roots is because it's a mathematical equation. It has no concept of time. That means there's 2 solutions in the past for negative time, and there's 2 solutions in the future for future time. And obviously we can ignore the past solutions, but there's potentially 2 future solutions, because sometimes a fourth order polynomial doesn't cross the line 4 times, sometimes it's just 3 or 2. But let's assume it does have 2 crossing points. One of the solutions will be close to 0, which will be the shortest time, and one of the solutions will be further away from 0, which is the longest time. And I mean, if you can guess it, the longest time is the solution where it fires the paintball gun like a mortar up in the air, and then it hits the target when it comes down. And then the closest time is where it fires it more like a rifle, where it has a very small arc trajectory. And obviously that's the solution we want. Okay, so now we have this fourth order Moore's polynomial equation that'll give us our target leading part. So it'll give us, we figured out exactly where they're going to intercept. That means we can trace it back to what the turret has to aim for. But how do we solve this? And you all know the solution to a second order polynomial, the parabola, minus b plus or minus the square root of 4ac over 2b. That's easy. There's only 2 roots, and that you can memorize that formula. Turns out there is a closed form solution to a fourth order polynomial, and that solution is so long it won't fit on a single A4 page when you write it out. So other than me not typing all that in and debugging the code and making sure I wrote that right, we have to ask ourselves, do we truly need such an exact solution, a machine precision solution, when we already have so many other errors in our system? And the answer is no. We can probably just achieve it much faster with small iterations. So you all know, well, I'm assuming most of you know Newton's method, or simply just choosing a point and then looking, if I go this way, am I going higher? If I'm this way, do I go lower? And then choosing the next point, and then keep doing that until you reach somewhere that's close enough to the x-axis that you can say, good enough for an engineer, fire,
run,
and off the bullet goes. And that's what we're going to do. So basically, we have to choose a first starting guess point, because obviously if we choose 1,000,000 seconds, it's going to converge after like 3 or 4 minutes, and then eventually end up at the longest time, because that's the first crossing, which means a lobbing bullet. So no, and also we don't want to start at 0. I'm pretty sure we can do better than that, because it's going to have to travel all the way to where the actual interception point is. So our first guess is just going to be from the turret to the target's current position. That's going to be our first time estimate. So based on the bullet's velocity, the distance of the target, that's our first time estimate. And that'll be pretty close to what the solution probably will be eventually. And then within 2 or 3 iterations, you move your sigma, which is your error value, which in this case was about 5 milliseconds, because in 5 milliseconds a person would move that far, which means I was still within my error bounds for the tracking system, which, by the way, because our mechanical system was so accurate, we could divide the accuracy requirements up between the tracking and the control system equally. And then I said, well, if the tracking system stays within 0.2 degrees and the control system stays within 0.2 degrees, then we've met our accuracy requirements. So in this case, for the tracking system, 5 milliseconds means the person just moved like 3 or 4 centimeters, and that's still way within our accuracy requirements. So all I had to do was find the time of flight that was within 5 milliseconds of crossing the x-axis. And then in like 3 or 4 iterations, which takes the computer no time at all, you found your interception time, you found your target leading angles, the pan and tilt where it should aim, and now you can send those angles off to your control system. So how do you do that? And that's the next part. The next part is communication protocols. So communicating from the computer to the control system on your turret. The control system is going to be a microcontroller like an Arduino, but I didn't use an Arduino, I used some Renesas controller. I'll talk about it in the control system. So how are these two going to communicate to each other? So I chose USB serial, and you want it to be really fast because it's a specialized communication port. You don't need to have massive handshakes and checks. You want to basically stream commands the whole time and make sure the turret is up to date with the closest approximation of stuff you just worked out. What's nice about the target leading algorithm is that any communication lag from the computer to the control system in the turret can also be compensated for, because you can simply add that lag to your target leading equation and it will push your trajectory even further ahead. So it'll compensate for the time it takes for the computer to communicate with the control system. So I'm going to skip some user interface stuff, how I design the user interface, like breaking it down into components of image processor, the controls, the safety checks and stuff, and then just go to communication protocol. So I basically chose all my communication packets should be 13 bytes, and then it has a start byte of exclamation point, and then a command character, and then the data packet, and an end character of a colon. Not a colon. A full stop. Is that a colon? No, because a semicolon is a thing that goes. A colon is 2 full stops. 1 full stop. That's the end of the packet. So, for example, aim would be exclamation point A, and then I'll have 10 bytes of data, which I split the first 5 into pan data and the last 5 into tilt data, and then the turret knows what to do with that. The control system knows how to interpret that. And the same with fire, reload, stuff like that. So the reason I have fire on here is because I can manually control the turret as well. So I can literally point on the screen and the turret will aim exactly where that point is in space, and I can basically fire like in a video game in range to test the gun. I didn't actually take a video of that. I should have, but I was too obsessed with the auto aiming. So yeah, that's basically what the tracking system consists of, and then hopefully in a shorter period of time I'll have the control system up and running, the control video up and running, and then the final demonstration and explanation of the whole system.